Hey everyone, and welcome. Today, we're diving into a really powerful tool in the world of string algorithms, the Suffix Automaton. Seriously, if you ever find yourself needing to process text in complex ways, this is one data structure you absolutely need to know about.
Okay, so let's just jump right in with a wild idea. What if you could take every single possible substring of a text, all of them, and compress them down into one single, tiny, super efficient machine? I know, it sounds a little like magic, right? Well, that's pretty much the core promise of a suffix automaton.
So, here's our game plan. We'll start with what this machine even is. Then we'll look at how to build it, what you can do with it once it's built, and of course, the key stuff you'll want to remember for your next interview.
All right, let's get into it. First things first, what exactly is this ultimate substring machine? Okay, so the official textbook definition is that it's the minimal deterministic finite automaton, or DFA for short, that recognizes all the substrings of a string. Now, a DFA is just a simple state machine. You give it a string, it reads it character by character, and spits out a yes or no. The two magic words here are all substrings, it knows about every single one, and minimal, which means it's the smallest, most compact way to represent all that information. No wasted space. That formal definition is cool and all, but to really wrap our heads around this, we're going to need a better mental model. So let's build one.
Honestly, the best way to think about a suffix automaton is to picture a map. It's like the smallest possible roadmap that has a specific path for every single substring in your text. On this map, every state is like a city, and each city represents a whole group of substrings. The thing they all have in common? They all end at the exact same places in the original string. This idea is formally called end-pos equivalence, but city is way more intuitive, right? And of course, every map needs roads. The transitions are the roads that connect our cities. Each road has a label, a character. So if you're in one city and you take the road labeled A, you're basically just tacking an A onto your substring and arriving at a new city. Simple as that. Now here's where our map gets really cool. It has these special paths called suffix links. You can think of them like secret back alleys or shortcuts. A suffix link points from the city you're in to another city, one that represents the longest suffix of the substrings in your current city. This little shortcut is the secret sauce. It's what makes the whole thing so compact and so fast to build. So how do we actually build this incredible map? Well, the algorithm is a thing of beauty. It's online, which means we build it one character at a time as we read the string. And the best part, it's ridiculously fast. It runs in linear time. So for each new character we add, we follow 5 basic steps. First, we create a brand new city for our new, longer string. Then, we use those suffix link back alleys to trace our way back and add new roads. Step 3, we have to check if this created any conflict with path links. If it did, and this is the clever part, we clone an existing city. And finally, we just redirect some of the old roads to point to our new cloned city.
Okay, I know what you're thinking. Cloning? That sounds weird. Why would we need to duplicate a city on a map that's supposed to be minimal?
It's actually a really elegant solution to a tricky problem. Sometimes, when you add a new character, you create a situation where one path represents substrings of different lengths. That breaks the rules. So, cloning splits that problematic city in 2. It's a surgical fix that makes sure our map stays both minimal and correct. And the result of all this careful work? A structure that's just shockingly small. For any string of length n, you're guaranteed to have, at most, about 2 times n states and 3 times n transitions. That is an incredibly tiny amount of space to store information about every single substring.
So we've built our map. Now for the really fun part. Let's actually put it to work. This is where the suffix automaton really starts to blow your mind.
And here is the payoff. Want to check if a pattern exists in your text? You just try to walk the path on the map. The time it takes is proportional to the length of the pattern, not the text. It's super fast. Counting every unique substring? Just one quick pass over the map. You can see the pattern here. Almost every classic string problem becomes blazingly fast.
Now, a common question is, hey, how is this different from a suffix tree? And that's a great question. The biggest difference is what they're built for. A suffix automaton is the minimal machine for all substrings. A suffix tree, on the other hand, is built specifically for suffixes. They can solve a lot of the same problems, but the automaton is often smaller and, by its very nature, the most compact machine for its job.
All right, let's bring it all home. Let's boil this all down to the absolute must-know points for when this topic comes up in a technical interview.
Here are the 4 things you want to have locked and loaded. First, really understand why cloning is necessary. It's all about keeping the machine minimal and correct. Second, know the basic idea behind counting things, like how the path links relate to suffix link links. Third, be ready to clearly lay out the difference between an automaton and a tree. And finally, a pro tip. Mention that some queries, like counting occurrences, need a quick extra step after you build the main structure.
If you walk away remembering just one sentence, make it this one. The whole thing is built on these 4 pillars: the goal of being a minimal machine for substrings, the idea of grouping strings by where they end, those clever suffix link shortcuts, and the super efficient algorithm that ties it all together.
And there you have it, the Suffix Automaton. It's way more than just a niche algorithm, it's a really fundamental tool for working with text. Its applications are everywhere, from DNA sequencing to checking for plagiarism. So the only real question left is, now that you've got this ultimate substring machine in your toolkit, what kinds of problems are you going to go solve?